Hello, dear student. I hope you are doing well. In today's lecture, we are going to talk about hydraulic jump. This is lecture 13, and we now are going to start chapter 12 of our textbook. Uh, the entire chapter is about hydraulic jump. You know that we already mentioned about the definition of hydraulic jump, which is an abrupt change from a shallow high-speed flow to a deep low-speed flow of lower energy. We mentioned that this is a case of rapidly varied flow, and here you see some examples. For example, here along a wetland, we have a shallow rapid flow which reaches deep flow. We have a supercritical flow condition here, and due to the higher depths, we have a subcritical condition here, and you see hydraulic jump. This is the interaction between supercritical flow and subcritical flow. This is another example when you are doing dishes. You might see in the sink that when you open the faucet, a very thin layer of flow, which is called sheet flow, appears here with the height of 1 or 2 millimeters. It is very quick, but here we have higher depths with lower velocity, and at the boundary of this sheet flow, we will see hydraulic jump. In which water change its velocity from supercritical velocity to lower velocity of subcritical flow condition. This is another case of hydraulic jump, in which the hydraulic jump happened here as a result of sudden change in the bed elevation. In this case, or sudden change in the base elevation, in bottom elevation of a natural rivers, was already discussed in chapter previous chapter, and today we will consider the hydraulic jump when liquid at high velocity discharges into a zone that has lower velocity. These are some examples, some situations that hydraulic jump appears in the rapidly rapidly varying flow condition. In case A, you see that we have a supercritical flow. This is YC. Yes, sorry. Yes, this is YC. The dashed line shows the location of critical depths in all figures. This is dashed line, and this is the critical depths location. As you know, in when we have depths below critical depths, the flow regime is supercritical, and when we have depths higher than critical depths, flow regime is subcritical. In case A, you see that we have a supercritical flow condition or supercritical flow within a channel which has bed slope greater than critical slope, which is called also a steep slope. When this flow reaches to a bed with a slope less than critical slope, which is also called mild slope. We already talked about it at the beginning of the lectures about rapidly varied flow. You see that in this sudden change from supercritical step to subcritical step, before the location of the sudden change, we will have hydraulic jump, in which the flow depth wants to increase its depth suddenly or rapidly to have a normal depth to be above the critical depth. In figure B, you see the sluice gate. This is a sluice gate that decrease the cross-sectional area of flow of upstream. You see, for example, we have, for example, a rectangular cross-section here with a depth of y0, which is higher than critical depth. Therefore, we know that here we have subcritical flow condition. By decreasing the cross-sectional area using this sluice gate, what will be happen? Flow velocity at the bottom of the sluice will increases, and therefore we will have supercritical flow here. Also, you see that the bottom is to some extent horizontal bottom slope, or as you see here, bottom slope is less than SC, or this is the slope is below the vertical slope, which is also, as I said, it is called mild slope. Therefore, in mild slope, we can increase flow velocity using sluice gate. When it increases, you know that if we remove, or if in the experiment we don't have a sluice gate, water profile, surface profile would be something like this, yes. And without the sluice, we will have, if it is uniform flow, the y0 will be constant along the entire channel. But by pushing a sluice gate, putting in a sluice gate here, uh, at the beginning of the experiment, water level at downstream will start to decrease, and to reaches to here. Yes. However, after a while, water hydraulic jump will happen here, and again we will have increase in the surface of water, and water, as I already talked about it, flow would like to have a subcritical regime, and by the help of a hydraulic jump, this phenomenon will be happen. Another case is case C, this case, in which a hydraulic jump appeared above at the upstream of the sluice gate. Then we have critical flow supercritical flow regime. As you see, the flow or flow depth is less than critical depth, either in the upstream or in the downstream of the sluice gate. A hydraulic jump happened at the upstream, and we have a rapidly varying flow, where the flow at the upstream height of flow or depth of flow increases to be more than a critical depth. And the last example is flow over an spillway. This is an spillway of a dam. We have subcritical flow above at the upstream, and then we have a quick shoot flow, which is very fast flow, and here hydraulic jump appears at the downstream of spillway, and um, again flow depth increases to be more than critical depth. Therefore, these are some cases that we can see hydraulic jump in practice. Uh, it is useful to mention that the triggering of a hydraulic jump at the base of a spillway is desirable to remove surplus kinetic energy in order to reduce downstream erosion. In this figure, you see the Norras Dam at Antalya, where this is our spillway. We saw a spillway in Paris example. When we have a flooding situation, water depth at the reservoir increases, and we will have release above the spillway, and at the bottom of a spillway, you see here, we have a sudden change in the from steep to mild slope. Hydraulic jump appears like this, and through this hydraulic jump, lots of the energy in the water will reduce, and by reducing this, as a result of this uh, loss of energy, the erodibility power of the water will decrease, and we can have a safe downstream and safe bottom at the downstream of the spillway. As you see here, this is for example, this is our spillway. Very quick, fast flow comes, and here we will have hydraulic jump. This is called also a stealing basin, where water comes to have a lower energy, and about depths of the flow before and after hydraulic jump. We can define an initial depth, which is the depth before the hydraulic jump, and we will have a sequent depth, which is the depth of flow after hydraulic jump. So by definition of hydraulic jump, and we see that in some cases it is useful uh, for practical works in hydraulics engineering. And what is our aim actually in this lecture is to find different characteristics of hydraulic jump. For example, we see here a hydraulic jump, and we are going to know the depths, initial depths y1, the sequent depths y2, and as I told, due to hydraulic jump, we have considerable energy loss, so we are interested to know what is the amount of loss of energy when water from a supercritical condition jumps to a subcritical flow regime. And also the interested question is the length of hydraulic jump. This is the length of hydraulic jump is the length between the initial and sequent jumps, which also called conjugate depths. Sorry, initial and sequent depths, which are also called conjugate depths. From the energy equation in open channel flow, you remember this equation that we said specific energy at section 1, for example here, equals to this is a general formula plus z1, which is the elevation of the first point or bottom of the cross section 1 from the datum equals to specific energy plus Z2 plus loss of head between two cross section. And for the case that you remember, for the case that uh, mm, we can, for the case of horizontal flow, we can remove Z1 and Z2. Therefore, we had specific energy at section 1 equals to a specific energy at section 2 plus HL. It is head losses. And for the sudden, for example, for the case of sudden transition, because of the short lengths and short lengths of the channel between two cross sections, we said that we can neglect HL because of the lower magnitudes of friction force between two cross sections. However, in the case of hydraulic jump, we will have considerable magnitude of energy losses. Therefore, we cannot say that E1 equals to E2. By this, I mean that when we have a hydraulic jump, energy is not conserved, but we know that mass is conserved. Therefore, instead of the conservation of energy, we can use conservation of momentum because the mass between two cross sections, section 1 and 2, always conserved. So the principle which we'll use to find these unknowns y1, y2, and also L can be derived using the momentum equation. And momentum equation is nothing than net force, sigma F, or sigma F of external, equals to rho Q delta V. You are familiar with this formula and its derivation that we already talked about in fluid mechanics. Therefore, we are going to use this equation to find our initial and sequent depths in a hydraulic jump. If you remember, when we want to use momentum equation or conservation of momentum, we create a control volume. And then we should find the forces acting at different sides of our control volume or control surfaces, and finally the net force would be equal to rho qv2 minus v1, or you remember we said that rho qv output minus v of input. Here this is y1. This is my hydraulic jump, and I assume this volume as a control volume, and you see my control surfaces. However, before going to solve or show the acting forces on this control volume, I must mention that we assumed short horizontal reach. As you see, it means that delta L, or distance between 1 and 2, is short, and this is horizontal. There is no slope. Therefore, we can neglect the gravity force. We have a theta 1 gravity force in the flow direction, should be considered in the calculation of net force. However, when we say that this is a short length and no theta, therefore we do not have the gravity force in x direction if it is our x direction. On the other hand, when we say that this length, distance between 1 and 2, is short, therefore friction force or FF is negligible, and in X direction we would have only pressure force at upstream and downstream, or at initial and sequent depths. The other assumption here is the assumption of the hydrostatic pressure at both upstream and downstream. As you see here, we assume we have a linear distribution of the pressure at both upstream and downstream, and um, from the dynamic pressure as a result of the moving water, we neglected because its value is also not significant, and we can neglect it. Therefore, what we have as a force at this control volume, we have a positive force along the flow. Our input, our positive or V1, is the force of this pressure, and we have a negative force, negative because it is in front of flow direction, this triangle. You know that pressure, if this is our pressure distribution, force is pressure times the area, yes, like what we did in fluid mechanics. And to calculate corresponding force of this pressure diagram, we should find pressure at centroid, yes, pressure at centroid multiplied by area. And we said P bar 1 multiplied by area at upstream minus P bar 2 pressure at the centroid of downstream area multiplied by the area, surface area of the downstream, and P1 A1 minus P bar 2 A2 is our net pressure force. Therefore, we find the left hand side of this equation, and we know the right hand would be rho Q V output, which is section 2 V2 minus V1 at extraction. So, what is the definition of pressure? Again, we know that if the case is hydrostatic, we can say that pressure equals to gamma HA. You remember, or gamma HG multiplied by area, or gamma YG multiplied by area. YG is the depth of the centroid from this water surface. Yes, this is at upstream water surface. Here, depth YG would be half of the y1, and also yg or y bar at section 2 would be half of the y2, and so I can replace p1 with gamma y bar 1 and p bar 2 with gamma y bar 2. Gamma is the density of the liquid, or which is water here. And for the case of right hand side of the equation, we have rho Q V2 minus V1. Therefore, we can say that minus rho V1Q plus rho V2Q. And you know that this charge is along the this charge is constant along the hydraulic jump. So here I replaced gamma with rho G, and y bar, as I told, it is half of the y1, and y2 is the half of y2. And I have rho term here also, and I can, instead of this equation, can show such equation: half of rho g a1 y1 minus half rho g a2 y2 equals to minus v1 q plus rho V2 cubed. And you see I showed that this is xv at x direction. Oh, you remember these are vector of the velocity vector, and all the calculations in this slide were done in x direction. So this is the conservation of mass or conservation of momentum in hydraulic jump, which would be very helpful to find our unknowns. Yes, the previously shown formula can be written as here, as you see here. Uh, 1/2 of the rho g a1 y1 minus a2 y2 all in parentheses equals to minus rho q square over a1 plus rho q square over a2. And if I can rearrange this equation and divide both sides by rho g, therefore I will have um, uh, all the parameters relevant to initial depths in the left hand side and for the sequent depths in the right hand side. As you see here, I divided both sides by rho g, therefore uh, I have a g term here because I have rho and I have a g built at the denominator of q terms, and this is the results. Q square over g a1 plus a1 y1 divided by 2 equals to q square over g a2 plus a2 y2 over 2. And we also know that y1 over 2 and y2 over 2 is the y bar, yes, for the depth of flow at the centroid of the cross-sectional area. And this equation is very important equation in hydraulic jump problem, which each of these terms has their own meaning, and some of the q square over g a1 plus a1 times y1 is called specific force. You remember this equation is so similar to the energy, specific energy term where we had y and v. Yes, we had y and v, y plus v squared over 2g, and here we have multiplication of those terms in area. Therefore, the unit of each term here is cubic meter. Yes, y meter, area is in square meter. Each term has the unit of the cubic meter, and the sum of a1 y1 a1 y bar 1 plus q square over g a1 is called specific energy, specific force at cross section 1 or at initial depths, and this is my specific force at sequent depths. Okay, this is a general formula with some assumption, and you remember that at the beginning we assumed, for example, the length is short, there is no slope, and some other assumptions. But for the case of rectangular cross sections, we know that A equals to by. In this equation, we want to replace A with by, and we already defined the unit discharge or discharge per unit width as a Q over B, or total discharge divided by the width of the rectangular cross section. If you replace these two terms in this equation, you will reach such equation: q square over g b1 y1 plus by square. Instead of I wrote by, and I have a y1 divided by 2. Yes, y bar is y1 divided by 2. Again here, y bar 2 equals to y2 divided by 2. When you multiply it by by as a here, or by2, here by1, this is the new form of the specific force at rectangular cross sections. I think we can more simplify this equation, because we also we still, or we didn't change the use the unit discharge yet in this form. So what I did, I replaced all the terms of q with q over b. Yes, with q over sorry, q times b. Instead of q, instead of capital Q, I can write b times q. If b is constant in both upstream and downstream, yes, b is constant. Therefore, that if you see b1 here is a typing error. Yes, don't think about b1, because b is constant at both upstream and downstream of a hydraulic jump. And if I wrote here, instead of q bq, the b term will remove from will cancel out from both up and down of the this fraction. Therefore, the resultant equation is b-less, free from the appearance of b term. And in here, I have y1, and then I move this y term to the left hand side and move this q term, yes, q term to the right hand side, and this is my resulting uh, formula for rectangular cross section, which shows a relation, a mathematical relation between y1 and y2. And this is a if I solve this equation for you, for y2, I can find a relationship based on y1 and q for y2. So one of the unknown, which is y1 or y2, can be found using this formula. When you know y1 and discharge for a given discharge, you can find y2, and vice versa. If you know y2, you can find y1. As I already told, y1 is initial depth, y2 is sequent depth, and both also are called conjugate depths. Here I rewrite the last equation that we derived for a rectangular cross section, the relationship between the conjugate depths, and I'm going to uh, a bit simplify this equation using some known facts or formulas in rectangular cross section. Rectangular cross sections, you know that critical depth is third root of the q square over g. Yes, this is the magic formula that we can use in rectangular cross section to calculate critical depth. So I can replace this term q square over g. Yes, I have q square over g. Instead of this q square over g, I can use yc. Yes, however, this is yc to the power of 3. It should be yc to the power of 3, because I have 1/3 here, power of 1/3 here. Therefore, the new form of the relationship between the conjugate depths is y2 equals to y1 over 2 times minus 1 plus square root of 1 plus 8 yc over y1 to the power of 3. So for a rectangular channel, if you know, for example, yc and y1, as we showed in the previous figures, that, for example, we know y1 at upstream and we know the critical, or we can calculate critical depths for a given discharge of a rectangular cross section. Y2, or depths of or sequent depths, can be calculated using this equation. The other method for simplification of the original formula is the use of velocity as a q over y, yes, because q equals to b times, or q equals q over b, and from the continuity equation you can find velocity as a q over y. Therefore, you can replace this q value with Vy. If you put Vy, and you know this is y1, for example, at the cross section 1, this is y1, you can you will reach a formula that instead of q square over yc, by replacing v, you will reach such a formula where we have Froude number at the upstream. Therefore, by knowing the Froude number at upstream for a given depth of the initial depth, you will be able to find sequent depths of the hydraulic jump. Let's have an example to see how this formula can be used to solve a problem. In this example, a hydraulic jump forms in a rectangular open channel with a width of 2 meters, in which water is flowing at 4. It means that at discharge of 4 cubic meters per second. If the depth just downstream of the jump, sequent depth, is 1.25, as you see here, the question asks us to calculate the vertical depths of upstream at depths at upstream of the jump, y1. How we can solve it? Now this is the case of rectangular cross section. Therefore, either this formula or this one can be used to solve to find y1. However, we here the y2 is known and y1 is unknown. Let's see which formula I use to solve the problem. You see here that I first calculated the critical depth for this channel. For a given Q, which is capital Q over 2, and capital Q, as I told, is 4 cubic meter per second. B, or bottom width, is 2. Therefore, unit discharge would be 2 cubic meter per second per meter. And again, Q square would be 4, and G is 9.81 to the power of 1/3. And from this calculation, we will see that critical depth for this channel equals to 0.74. Yes. So this is somewhere here. Definitely, critical depth is below the sequent depth. And now, if I have this critical depth from these equations, I can easily use this one. For example, I repeated that equation here. Y2 equals to y1 times minus 1 plus square root of 1 plus 8 yc over 1 to the power of 3. And y2 is at hand, y1 is unknown, and I replaced value of yc here. Yes, this value here. And this equation must be solved for y1 to find y1. Uh, the common way to solve such equation is to use a trial and error method with some assumptions. For example, I started with y equals to 1. For example, you see I put 1 equals to 1, and I saw that for the case of when I assume 1, you see I put y here 1 and y here instead is here 1, and I calculated, and this term gave me 0.5, which is not equal to 1.25. Therefore, the initial depth cannot be 1 meter. I increased and checked for the 2, and you see that when I put y2 here and 2 here, the solution is about 0.18, which is far from than 1.25. It gives me a note that I'm in wrong direction. I have to reduce the value of y. Instead of 1, I should go to the selection of lower depths. What I did at this third step or third trial, I put y equal to half here and half here. I solved it and I see that the y equals to 1.04, which is a bit close to the 1.25, and then I again reduce the value of zero point 0.5 to several values, and I saw that for the case of 0.39 or zero point 0.4, let's say zero point 0.4, the right hand side equals to 1.25, which is so close to the value of sequence depth in my hydraulic jump. Therefore, the answer of y1 is 0.3 or 0.4. By this slide, we were able to calculate y1 and y2, which were our unknowns in the problem of hydraulic jump. However, the other unknown is the magnitude of head loss, uh, which we said is very important in the hydraulic jump problem. This is again that hydraulic jump, and to calculate or estimate energy loss along a hydraulic jump, we can again come back to the conservation of energy, the general rule of conservation of energy, which says that specific for the horizontal, for example, sections, horizontal channels, specific energy at section 1 equals to specific energy at section 2 plus energy losses. Here, energy losses is those of amount of loss which appeared as a hydraulic jump. We told this is not a function of friction at the bottom. This is only the feature of hydraulic jump, which is the loss mainly due to the turbulence, water, and viscosity and effect of uh, air bubbles when they goes to the water and they reduce energy of the liquid. So energy, specific energy at both, when you know y1 and y2, using previous formula, you were able to find these conjugate depths. You can, when you know the discharge, you can calculate velocity at both sides. Therefore, energy terms can easily, specific energy terms uh, can easily calculate it with respect to the even continuity equation or the relationship between y1 and y2. The only unknown in this formula is HL. Yes, head losses. For the previous example, if I assume y1 equals to zero point 0.4, I can calculate specific energy. H1 here is E1. Your book showed with H, but actually we in this lectures we said E1 energy. Yes, energy at specific energy at cross section 1 equals to y1 plus v1 square over 2g equals to 1.69, and the same formula with the values of y2 and v2 gives you a specific energy of 1.38, and you see that we have about 0.3 meter loss of energy when we have hydraulic jump, and 30 centimeter head loss uh, was happened. Okay, this by this slide also we now found our third unknown. Let's say second unknown. If the first unknown was the depths of the uh, initial or sequence depths, the second was the head losses, and the last unknown was the length of the hydraulic jump or energy length. Uh, about energy losses, I also, before going to the length of the jump, I would like to present another formula to calculate energy losses. This is our general rule, yes, E1 equals to E2 plus HL when we have energy loss. For the case of hydraulic jump, in rectangular channels, you can write energy specific energy with y plus q square over 2gy square, yes. And if you do some algebra, you can find HL. You know, this is E for E1 and E2. Repeat this formula. HL with in terms of y1 and y2. The proof of this equation is something that I want you to do at home and check if the formula is true or not. Anyway, this is true, which shows head losses at hydraulic jump at rectangular cross sections. And for the case of length of jump, I have to say that there is no general theoretical solution for the length of the jump or distance between the initial and sequence depths. Experimentally, we know that this length is 6 times greater than the sequence depth. This is for the case that third number at the section 1 is something between 4.5 and 13. Yes, dear students, that's all about hydraulic jump. I showed you how we can calculate energy losses and conjugate depths using the theory of conservation of mass. And by the end of this lesson, you are able to solve all the examples or the questions or problems at the end of chapter 12 of your textbook. Have a good day. Thank you for listening.